We concisely overview our recent ICLR paper where we developed spherical CNNs that are both computationally scalable and rotationally equivariant. Data on the sphere arise in many applications. For example, in cosmology, observations are made over the celestial sphere, while 360-degree photos and videos are also observed on the sphere. To transfer the remarkable success of deep learning to applications involving spherical data, we need deep learning models defined natively on the sphere. And just as planar CNNs encode translational equivariance, one of the key factors responsible for their success, spherical CNNs should encode rotational equivariance. Current spherical CNN frameworks can be broadly classified into two categories. Continuous approaches constructed natively on the sphere, typically through spherical Fourier representations, exhibit excellent rotational equivariance properties, but they are not computationally scalable at present. Discrete frameworks necessitate an approximate representation of spherical signals, losing the connection to the underlying continuous symmetries of the sphere, and thus cannot fully capture rotational equivariance. However, they can typically be computed efficiently. In this work, we introduce a hybrid discrete-continuous framework, which we call DISCO, that is simultaneously rotationally equivariant and computationally scalable. The DISCO approach follows by a careful hybrid representation where some components are left continuous to facilitate accurate rotational equivariance, while other components are discretized to yield scalable computation. The continuous convolution on the sphere is defined analogously to the Euclidean setting, where we pass a filter psi over a signal or data f, taking the pointwise product before integrating. We carefully approximate this by the DISCO representation. We appeal to a sampling theorem on the sphere to capture all information content of the signal in a finite number of samples and to evaluate the continuous integral accurately by quadrature. The filter and rotation are treated continuously to avoid any discretization artifacts. In this manner, the underlying continuous spherical convolution can be evaluated highly accurately through a hybrid discrete-continuous approach. While the DISCO spherical convolution is already computationally efficient, we achieve further computational savings by restricting rotations to the quotient space SO3 on SO2, which is isomorphic to the sphere, eliminating rotations of the filter about its own axis. However, since the resulting quotient space is not a group, important differences to the usual setting arise. For rotations in SO3, the DISCO spherical convolution is fully rotationally equivariant. However, this result relies on the group structure of SO3. For the restricted space of rotations, equivariance does not hold due to the lack of a group structure. However, we do recover asymptotic equivariance in the limiting case where the latitudinal rotation approaches zero. This is actually of significant practical use since content in spherical signals is often orientated, with similar content appearing at similar latitudes, particularly for 360-degree panoramic photos and videos. We validate the full and asymptotic rotational equivariance properties of the DISCO representation through numerical experiments, finding equivariance errors are less than 1%. We introduced a scalable implementation of the DISCO spherical convolution through a sparse tensor representation, with a compressed representation to reduce memory, and with custom sparse gradients. Our approach achieves linear scaling in number of pixels on the sphere for both compute and memory cost. The DISCO spherical CNN framework thus achieves excellent rotational equivariance while also being highly computationally scalable. It can therefore be used in architectures with high resolution input and output layers as needed for dense prediction tasks. In the following dense prediction benchmark problems, we can consider a common backbone of a residual U-Net architecture based on DISCO spherical convolutions. First, we consider the recently introduced Pano 3D depth estimation benchmark problem, where we predict depth maps from 360-degree RGB images. Compared to the benchmark of a deep planar U-Net, we achieve state-of-the-art in 6 of 9 metrics with 40 times fewer parameters. We also consider the task of semantic segmentation on the 2D 3DS dataset of indoor 360 RGB images. We again achieve state-of-the-art performance on this benchmark problem compared to a number of alternatives. To conclude, we have developed a hybrid discrete-continuous, or DISCO, framework for spherical CNNs that is simultaneously computationally scalable and rotationally equivariant. Our framework also generalizes straightforwardly to other geometries. We have applied our approach to a number of benchmark dense prediction problems on the sphere, on all of which we achieve state-of-the-art performance. The DISCO layers provide the building blocks needed to realize a host of modern deep learning models, such as generative models, on geometries like the sphere and beyond.